Hello, friends. I'm not going to have the camera on for a number of reasons. One of them is I look like a guy who's been laying in the same clothes for half a week with COVID. I cleaned it, but I'm not looking great. I just don't feel like being on camera. So this is going to be a whiteboard presentation. We're going to cut to Desmos a few times. And it's super helpful. And I'm going to actually ask you to maybe open up Desmos while you're working through this lecture with me. And I'll occasionally be sipping tea, but you're used to that. So today's topic is optimization. When you first did this back in Calc 1, you would be given some function like f of x equals x squared minus 4x plus 4, and you'd be asked to find the max or min. And then you would be asked some other questions like, is it a global max or min, or is it a local max or min? And the way you proceeded with this was to find first, so the first step was to find the first derivative and set it equal to 0 to find the critical values. Now, there's also other critical values where f prime of x is undefined. And it essentially, though, that probably means that f prime is a fraction and the denominator blows up at some point. That can happen in the events that you had a function with a cusp like that, that the derivative at this peak right here is undefined because think of all the tangent lines that could balance upon that peak. But it is definitely a max. So when that first derivative is undefined, you can have a max and certainly or a min, and certainly we're used to the more classic. I've just got a single horizontal tangent line where the derivative is equal to 0. Here's where it's undefined. And then you would first set f prime of x equal to 0. And if that didn't have a solution, or even if it did, you'd make sure that the denominator did or didn't have a 0. In other words, you check both these conditions. You'd get a list of critical values. And you would then move to what was called the second. So this is the first derivative test. It's more of a necessary condition. The first derivative test actually would be where we look at the sign, SIGN, of the first derivative in areas to the left and the right of a critical value. So, for example, in this one here, if maybe I located that critical value C, I could look at the value of f prime to the left of C and see that it's positive, and then the value of f prime to the right of C and see all those tangent lines have negative slope. And from that, I could gather that I had a max right there because on the left we have positive slope, on the right we have negative slope going up, hitting the peak, going down. That's the first derivative test. But this is, I guess I'm moving to this pink here. This f prime of x, these critical value findings, this is necessary conditions for an extrema. Good Lord, can't even spell conditions. COVID's rotted my brain, friends. Anyway, spelling was never my strong point, but we would look for the potential critical values, and they weren't always maxes or mins. So for example, if you look at good old x cubed, you can see that you have a horizontal tangent right through zero, or you might want to do the first derivative test and see that you do have that tangent slope of zero when x is zero. Now, I keep saying first derivative test, but I don't really mean that. You would just look for the critical values, and you would see you have one at zero. But that's not a max or a min. It's just a place where the curve levels out for a little bit before continuing to climb up. So if you couldn't graph the function, how could you discern if you had a max or a min? Well, then you would go to the second derivative test. And I'm going to go back to blue here. Second derivative test. And let's see, what kind of pages do I got here? I think this page is, sorry, I'm using some software that is funky. Well, I guess I'll have to go to a new page. The second derivative test assumes you've already found a critical value C. And that's some x value where the first derivative is either undefined or set equal to zero or goes to zero. And then you would plug that into the second derivative. And if the second derivative was positive, that meant you were concave up and you had a minimum. If the second derivative were negative, that would mean you were concave down and you had a max. And if the second derivative was zero, you didn't really have any information and you maybe needed to do some deeper analysis. And that deeper analysis might be going to that first derivative test and just looking, am I increasing or decreasing on the left? Am I increasing or decreasing on the right? And working from there. But this is a sweet, easy test to quickly categorize our max min values. Now, I think I'm going to ask you to, and I think I already did ask you to read through the section on optimization in our book, Active Calculus, multivariable version. So please go read and refresh your mind on all these terms like relative max min, absolute max min, because I'm not going to go through those today, but you can easily read what those definitions are. Those are all examples of what are called extrema, extreme values of a function. Okay, so this is how you do it for a function of one variable. We have multiple variables, and we're really only going to stick to the two variable case. I've got a function. Sorry, I lost my pen. I've got a function f of xy, and I want to find all extrema. In other words, all local maxes, mins, and possibly those could be absolute maxes and mins, if there are any, and there might not be any. Since we have multiple variables here, things can get a lot weirder in the way a critical point can manifest. So we don't just have maxes or mins, we've got something in between called a saddle point, and we'll get to that. And you can certainly read more about that in the book. I'll definitely talk about it here today. So optimize this function f of x, y. I've got these two inputs. What is the greatest output I can get, and what is the least output I can get? So how do we proceed with this? Well, let's work through with a specific example. Let's say I have f of xy equals x squared minus x times y plus y squared plus x minus 2y. Now I'm going to ask you to go to Desmos 3D. So that's desmos.com/3D. I don't think I'm going to switch over to my computer monitor. It's too big a pain in the ass from the iPad I'm using. And I don't have Desmos 3D rigged up on here. So go to this address and graph this function. This is your z, of course, here, the output, and see what you get. And you maybe want to pause this until you can get that, because I am going to talk about it a little bit. Whoops, I'm thinking of level curves there. What you will see is you're going to see what's called a elliptical paraboloid. I think that's right. It's not parabolic ellipsoid. No, it's a elliptical paraboloid. And ooh, that axis doesn't go there. This actually kind of sits back in the fourth quadrant where everything is negative. So if you've got X, Y, and Z like this thing is in the back here. It doesn't look like it the way I've drawn it, but it's in that back quadrant where X and Y are both negative. And you see it's got this elliptical shape to it. It's horizontal slices or ellipses. And from the side, it looks like a parabola. So that's where that elliptical paraboloid term comes from. So we can see that there's a minimum here. And we could estimate it by using Desmos. But what we want to do is actually do it with calculus. And the process is going to be very similar to what we did in Calc 1. But since there's more variables, we fully expect complications. So first thing, let's just kind of go through the steps here, and then let's do it. So how to find extrema for f of x, y. Step one, we're going to essentially do the necessary conditions, just like with the first derivative conditions for a critical value. And here, the gradient is what takes the place of, of the first derivative being set equal to 0. So we're going to set the gradient of f, and that'll still depend on f and y, equal to, now remember the gradient's a vector, so we're going to set that to 0, 0. What does that mean? Well, remember that the gradient is the partial of f with respect to x and the partial of f with respect to y in the second component. And that's what we're getting set equal to 0. So I'm going to put the word set there, set 0, 0. And the only way those two vectors can be the same is if their components are the same. So this implies that we need, so we'll say here x naught, y naught is a critical value of f. I don't like that arrow. If the first derivative, partial with respect to x at that point is equal to 0, and the partial with respect to y is equal to 0 at that same exact location. And we're going to put the caveat in here. And honestly, we're not going to deal with this case this semester, but you should be aware of it. Or one of these f vex, or, and that or is inclusive. It could be both of these, are f of y do not exist at x naught, y naught. How could that be? Well, imagine a giant cone. So that's kind of a big old cone right there. But imagine some kind of, a circus tent kind of thing. There's a sharp point on top. For this one, we can see that the extrema, the x naught, y naught, is right underneath that peak, but the first derivatives do not exist there. No directional derivative exists there. Think about all the tangent planes you could balance on top. It's just like with the cusps we saw in one dimension. So what your main thing you're going to need to worry about is setting those first partials equal to 0 and then solving them. Then solve the two equation two variable system for all xy values. All the places where both partials go to first partials go to zero, these are our critical values. All right, so we get our list of critical values. Let's do that for our example. So we had f of xy was equal to x squared plus xy plus y squared plus x minus 2y. If you want to pause and take a moment to find those partials, you could do it right now. And you either paused or you didn't, and you're watching me do it. So partial with respect to x is 2x plus y plus 1. Partial with respect to y is x plus 2y minus 2. And I'm going to set each of those equal to 0. And now at this point, I've got a system of two linear equations in two unknowns. And this isn't too bad to deal with. Let's call this first one equation 1. Let's call this second one equation 2. Lots of ways to solve this, and you probably know some of them. One is to solve one of the equations for one variable in terms of the other, plug that into the second equation to get a single equation in one variable, solve for that variable, and then plug that value back into your first equation to find, or your second equation to find the corresponding other variable value. But what I like to do here, especially in a case like this, would be to just use elimination. So I'm going to notice that if I multiply this second equation by 2 and then subtract, the x's will cancel out. So what does that mean? I'm going to take equation 1 minus 2 times equation 2. And what that's going to give me is 2x minus 2x, y minus 4y, 1 minus negative 2, which is 1 plus 2. So that's actually 3, that's 5. So let's see. Hold on, did I get the sign wrong? Yeah, no, it's positive 5. And check me out on that. Make sure you see how I got that. Because right now I can see that y, negative 3y is 5, negative 5, and so y is 5/3. So I got one of these. I could eliminate the other variable to get it, or I could just plug that value into one of these known equations to get the other variable. And I'm actually going to plug this into equation 2 because that just has x by itself. So immediately I'll see that x plus 2 times 5/3 minus 2 equals 0. And so that's x minus 10/3 minus, so plus 10/3 minus 6/3 equals 0. So that's x plus 4/3 equals 0. And I see then that x, the critical value for x here, or the x value of the critical point is x equals negative 4/3. And I think I said something originally about how this thing was in the back quadrant, and that is wrong. It's actually in the quadrant where the y-axis is positive, but the x-axis is negative. So apologies for that. I ain't gonna go back and refix it. I'll put some notes in the comment section for this video. So look, I've got my critical point right now. My x naught, y naught is equal to -4/3, 5/3. We'll come back to that in a minute. Just record that. We now know that if this thing has a max or min, a local max or min, or maybe an absolute max or min, it happens at that point. It has to. So how do we know if it's not some weird scenario where, just like with the x cubed, it just kind of flattened out and it's not really a place where we have a change of direction in every direction, you know? So if I was at a minimum point, think of what that would look like. If I was at a minimum point, every direction that I looked, I would move up. That would be a minimum point. That's not very, how about this? Every direction I looked into, and I moved in that direction, I would move up. That would be a min. If I had a maximum point and I tested every possible direction and I always moved down, then I would have a maximum. But we can't test every possible direction. And so the following test that we're going to take a look at is the second derivative test for multivariable functions. And it is a beyond the it is beyond this course for us to understand exactly why this works. I'll probably address it a little bit on Wednesday, but suffice to say, it it works for one, and it's a little more complicated because we do have two variables here. I will toss in some lingo that I don't think our book tosses in. So let's just get into it. It's enough hemming and hawing there. So the second derivative test works like this. We're going to find this quantity, D. It's called the discriminant. And it's actually, if you know some linear algebra, and you probably know some, at least as much as I'm about to say, because we've talked about it already, is the determinant of a very special matrix. So it's the second partial of f with respect to x, partial of f with respect to x, then y, partial of f with respect to y, then x, and the partial of f with respect to y, then y. Notice that the row of that matrix, that 2 by 2 matrix, the first derivative is the first variable. Well, sorry, in the first row here, the derivative is first derivative, partial derivative is with respect to x. Down here, the first partial is respect to y. When you look at the columns, you see that it's the second derivative that's with respect to x here, and the second derivative that's with respect to y here. So there's just a nice symmetry there that helps you kind of remember this. Now, we also know some other things, that most of our functions are nice enough that the mixed partials are equal. So probably fxy is equal to fyx. And we're going to use that in just a second. So what does the determinant of this thing look like? Well, I take that product there and negate it. So fxy, and I'm going to assume that that's fyx. So notice that that's just this times this is the same as one of them, and I'm just going to say it's the fxy squared, plus this product, which is fxx times fyy. And so that's our quantity D, and we're going to evaluate at the critical values. And let's call those x naught, y naught. And here's a prettier form of that discriminant. D is partial of f with respect to x, with respect to x at the critical value, times partial with respect to y twice at the critical value, minus mixed partial, either order, at the critical value, squared. Boy, that is some fine writing. We'll write that up again here. So in other words, d is equal to partial with respect to x twice, partial with respect to y twice, oops, minus mixed partial squared. That's a little better. I still almost didn't even make it, sadly. What a sad state I'm in. So we're going to plug our critical value into there. Now, this acts like the value of the second derivative for us, but more moving parts. So here's how our classification scheme will work. If this value at the critical point is positive, then you have to go check some other things. And if the second partial with respect to x at the point critical value is positive, then we have a local min. So here, the second partial is acting like the way you would expect it to. Then x naught, y naught is a local min. Else if partial with respect to x twice, that looks like a y, but I almost wrote a y, honestly. I'm not going to lie. Less than 0. If that thing is negative at the critical value, then, I can't even write then, x naught, y naught is a local maximum. Just like if you had a single variable function of x. Now, what happens if d is less than 0? Honestly, you should be happy because you're pretty much done. If d is less than 0, then we have what's called a saddle point at the critical value. And a saddle point, we've seen these before, is a place where in one direction you move upward, but in another direction you move downward. And so there's no max, there's no min. It's just a weird spot. Think again, I've mentioned this in class. The the region between two mountain peaks is a saddle point. And it's literally called the saddle between the mountains. And think of a saddle, right? There's no high point on a saddle if the saddle is infinitely big. Okay. So if d is less than 0, we're done. We know it's a saddle point. And if d equals 0, then the test is inconclusive. And here we would need deeper tools than we're going to be able to construct. So at the best you could say in this instance is, I don't know, maybe get a graph out, look at that point, do some deeper graphical analysis. We've got some pretty amazing tools these days. So now let's go back to our problem. And we had, again, writing it down. We had that function. We found the CV. There was only one critical value, and it was at -4/3, +5/3. And let's get those first partials out here, and or just find them again. So f with respect to x, f with respect to y. And we're going to find those mixed partials, or those second partials now. So f with respect to x twice is 2. F with respect to y twice is also 2. F with respect to x, then y is equal to 1. Now, I don't need the other mixed partial because I can look at everything here is so nice. You've got a nice polynomial in multiple variables, linear things in two variables. Sorry. Oh, excuse me. Hmm. Yeah, that's like an old man with COVID starting to peter out here just from writing and talking. So, let's find our discriminant. Notice that the discriminant does not even depend on a variable. If it did, we would have to plug in those critical values. But here, it's just going to be partial of f with respect to x twice times partial with respect to y twice. So this times this minus that mixed partial squared. And then simplify this. That's 3. That is positive. Since that is positive and second partial with respect to x is also positive, going back, we are at this condition right here. And we have a local minimum, which we saw. But now we've confirmed it mathematically, and we know the exact location of the point. So the next thing I would probably just summarize here is my results. Most of you are scientists. Even us mathematicians summarize things. Um, but we want to just give a nice little summary here. There is and this one is actually an absolute minimum now watch this, I have to actually plug these points, the negative 4/3, 5/3, back into the function and figure out what that's going to be. So I'm going to just do that right here. What is the actual output value? I need to tell my reader that. So we're going to have uh, x squared. Yeah, you're going to watch me do fractions. Sorry. Plus x times y, and you're going to watch me flip back and forth, or you're just going to speed through this. Who could blame you for that? And then plus the y squared. This isn't going to be too bad. And then minus x, plus x minus 2y. So plus minus 4/3 minus, do I say minus? Good Lord. Minus 2 times the y coordinate, 5/3. Let's crank that out. So we got 16/9 minus 20/9 plus 25/9. And then I'm going to convert these guys into ninths. So that's minus 12/9 and then minus 30/9 or plus 12. Nope, minus because it's negative 4/3 minus 30/9 because this here is 10/3. So that's 30/9. And working this all through, let's see what we're going to get. I got negative 4. Now comes the hard part, adding numbers together. Something ninths. So let's see, we've got negative 4, 21. 21 minus 12 is 9. 9 minus 30 is negative 21. There's a good chance of error happening here. And you know what would be cool? If you let me know there's an error here, I'll give you some extra credit on something. I'll give you a point or something. I don't know. I'll help you out. I'll do something for you. So if there's an error there, let me know. And I just freaking erased it. That's my error. I caught that one though. So we have this absolute max min of negative 21/9 at negative 4/3, 5/3. So you tell your reader what is the nature of the extrema, max, min, or saddle, and where does it occur, and what is the height at that point? All right, I got one last example here for you. And I'm gonna have to get my cane out and walk back to bed or something. So we got x squared minus y squared. That's our function. And let's go through the process. So gradient, 2x, negative 2y. Setting each piece of that equal to 0, you can see so quickly that the only way this can equal 0 is if x equals 0 and y equals 0. So our critical value occurs at the origin. Let's get that second derivative going, that discriminant. So we need second partial with respect to x, and that's going to be 2. Second partial with respect to y is negative 2. And the mixed partial with respect to x then y is 0. Interesting. So our discriminant is 2 times negative 2 plus 0 squared. That 0 comes from there. And that's negative 4. And I rejoice because I'm done. Since the discriminant is negative, we have a saddle at the point. And here I could actually just even give a triple. And the triple is going to be the x coordinate of the critical value, y coordinate. And this one's easy to evaluate. When I plug in 0 and 0, I get out 0. So I've got a saddle right at the origin. This actually wouldn't be too hard to see just with what we know. Notice that if y is equal to 0, I've got this no, I don't want that. I want pink. I've got this parabolic kind of activity going in the xz plane. And then if x is equal to 0, I've got this negative y squared thing going on in the yz plane. So as you move toward the x direction, you move up. If you move toward the y direction, you move down. So we have a saddle. And I didn't even spell saddle right. I just spelled it like Sade or something like that. All right, that's it. So I have put up a web work for you. So there is a web work that's up titled aptly optimization, and it's got some problems in it. Try to look at those before class on Wednesday, please. And I might have put some in there that I'm like, people should ask, if people are working on these, how could they not ask questions? Right? That's the kind of guy I am. So there's a few things in there that will be real brain teasers, and I'd love to chat about them on Wednesday if you want to. I'm also going to try to get uh, a pre-class problem created for you. It's not going to be here right immediately because I need to just kind of go lay down. But I will send you an email if I do put that up. But otherwise, please, 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 just go try some of the web work. You'll be really happy if you just get on this right now. That's it, friends. Thank you so much. Looking forward to seeing you in person. I'm going to have a mask on, which I'm not super stoked about, but I don't want to spread the joy to any of you. Kind of wish I had cooler masks. I've got these black masks that at the time seemed pretty cool, but I was like, man, I could go for a rainbow mask or something, especially these days for no particular reason. So be well, do some optimization, and I will chat with you all soon. And certainly email me if there's any problems with any of this, especially the web work. Take care, and I'll see you soon. Bye.